So now James Lee is going to give the first of 4 talks about his lower bounds for positive semidefinite ring.
Okay. Yeah, thanks for inviting me. Thanks for making the schedule so nice. All the preliminaries were set up yesterday. Also that I noticed Rick, I responded only 4 talks per day. It's also very nice. Okay, so we saw. Rick gave us already some idea of the connection between optimization and proofs that come up in this setting. And although I'll go through it again now briefly. And then Anupam, did some of the most difficult technical preliminaries. And L'Oreal gave us, already an outline of a classical, by which I mean like non-quantum version of the proof. So we're like in good shape to start. So so the basic object we're going to talk about is a polytope. D. We'll move on from polytopes very fast, but this is the motivation from optimization, which we can think of in 2 ways, right? As a bounded set of points satisfying some set of linear inequalities, and also, so this is the dual way to think about it, and also as the convex hull of a finite set of points. So this is a polytope. I'll even draw a picture. Here is I think that's a pentagon plane. And by the way, we have a relaxed pace, so you should ask questions, and if you like, we can even change the entire course of the lectures. Okay, good. So this is a convex hull of 5 points in the plane. Of course, you can also see it as the intersection of a bunch of half spaces. And then let's define maybe a notion of complexity for such a thing. This notation I'm going to use, you don't have to remember, it's only preliminary because we're going to prove it's equivalent to something else and then the notation will go away. But let's just define phi of p to be the number of facets of p. Okay. So phi here is 5, this thing has 5 sides. In general, a facet is a face of, if the polytope is full dimensional, let's just assume that it is, then a facet is a d-1 dimensional face. And why would you define this as a notion of complexity? Well, if you care about optimizing linear functions over such a polytope, then generically interior point methods can do this in time, which is polynomial in number of facets. So it's seems like a reasonable notion of complexity. Except for the fact that there are lots of things we would like to optimize over, except for the fact that they have huge numbers of facets. And one of the tools for getting around this is the idea of a lift of a polytope. So let's say that a polytope Q in some higher dimensional space is a lift of P. Basically, if P is the image of Q under a linear projection, if there exists mapping from a large dimension to a small dimension, which is an affine projection, which just means a linear map composed with a translation, such that P is the image of Q under that map. That's the definition of a lift. It means that you have a polytope sitting upstairs. It's a projection, you should think about n as being greater than or equal to d. There's a polytope sitting upstairs, and it linearly projects to P. And the point of this definition is that if you can, it's not hard. It's sort of a bit not our main focus today, so I won't write down the formula. But if you can optimize linear functionals over Q, then you can also optimize over P. So in particular, maybe it's possible that P has many facets, but there exists a lift of P that has only a small number of facets. And then you can optimize efficiently upstairs, allowing you to optimize efficiently downstairs. And this is a fairly powerful model of computation. It can do lots of cool things, but there's a sort of a natural lifted parameter to define here, which is the minimum number of the minimum number of facets over all lifts of P. So this is right. So the point is that we don't need P itself to have a small number of facets. If P is just the shadow of something with a small number of facets, then we can still optimize over it efficiently. It's an exercise. I mean, you can ask if you really want to see it. It's an exercise to see it. It's a very easy exercise to see that if you can optimize linear functions over Q, then you can optimize them also over P. And this contains, a lot of sort of linear programming theory for problems that have polynomial time algorithms. And as we'll see sort of later in the week, if we instead of insisting on exact lifts, we talk about approximate lifts, then I would say that a large bulk of the theory of approximation algorithms is exactly based on lifts of polytopes that you care about. There's a polytope P, it has lots of facets, so you can't obviously optimize over it, or maybe even it would be anti-hard to optimize over it. But there is a small lift which approximates P in some sense. So I'm just saying this is a powerful model of computation. Okay, so let's hold off on some examples for now, unless people really want to see one. I want to explain now the connection between this and proofs. Yeah.
Is there an upper bound on that after a certain dimension, the number of facets doesn't decrease anymore?
Yes. So if you're you only need to go up to. So first of all, if you have only d facets, then if you have only say k facets, then the dimension you need, the largest dimension you'll need for the lift is d plus k. Okay, that's one thing. And also, 2 to the number of vertices is an upper bound of the dimension of the facets. On the dimension of the lift you'll need. So, but the dimension is not really so important. It's really the number of facets that matters, because, like I said, if you can do it, if there exists a lift with k facets, then then you can already do it in k plus d dimensions. So, okay. But now, what's the connection to proofs? So let's define for a subset of R to the d. Let's define a plus of x. So this is just going to be the collection of all. Actually, let me define it slightly. Okay, so this is the collection of all restrictions of affine functions on Rd to x, but I want those functions to be non-negative on x. So let me write the description now. Again. Affine, and when I restrict it to x, I want it to be non-negative. So the only reason I write that is because I just want these things to be functions on the domain x, not functions on the domain R to the d. So these are just you just take all of the affine functions. Again, an affine function is just a linear function composed with translation that are non-negative on the set x. This gives you a family of functions. Okay? And actually, what I want to do is think about these as sort of a set of theorems that are true for x. Okay? So the theorem is that the function on x is non-negative, and then you take the whole collection, you get a bunch of theorems, and then you can talk about how to prove those theorems. And so let's state now what Yannakakis tells us in this setting, which is that for a polytope P, the set of affine functions that are non-negative on P is exactly. So first of all, by cone, I just mean all of the non-negative combinations of those functions. So you sum them up with. These things are. Sum them up with non-negative coefficients. I didn't say what the functions are yet. Okay, let's do it. Where fi of x is bi minus inner product ai x. And recall here that let's write it up here. So where this is the A1 through AM are the rows of this matrix A. So the point is that all of that, that's, okay, this is an affine function. It's a linear function and a translation. This function, by definition, is non-negative on the polytope because the polytope insists that all of its points have this function being non-negative. And Farkash's lemma just says that all of the non-negative affine functions on the polytope are conic combinations of the ones that define it. So, for instance, the ones defining this one are these five constraints there. And the point is, any other affine function which is non-negative on this polytope, so that the fact that this thing is on this side of this hyperplane, can be written as a conic combination of the defined ones. So it's and this is exactly the content of Farkash's lemma. It's yeah, go ahead.
Probably you need the constant 1 as well.
No, because since P is bounded, we don't need the constant 1.
No, but you need actually that P has non-empty interior.
Yeah. Okay. This is a good point. So let's assume that also that the interior of that P contains a small ball. In order for this to, it's true that if P were unbounded or the I mean, we don't really need we need using the relative interior to be non-empty. But it's true that if P were unbounded, it's not such a big deal. If P were unbounded, or it didn't, or its interior was empty, then you might need to add here also the constant. Then basically, you don't get the inequality 0 is less than or equal to 1 for free, and you have to add in the constant function there. But this is a small concern, so let's not deal with it. Let's just suppose that that P is full dimensional and non-empty. That doesn't make any sense. And the interior is non-empty. I mean, if you have a full dimensional polytope with an empty interior, that can't happen. So why would I even say that? So right. Once we say that it's bounded and full dimensional, we're fine. Does everybody agree? Yeah. Okay. Good. So this is okay. So in terms of proofs, Farkash's lemma tells us that sort of the defining inequalities are axioms that can sort of prove all of these theorems. So all the non-negative functions can be proved. What do the proofs look like? The proofs are just these lambda I, the coefficients, and then the fi's are the axioms. So a different way to say this is just that the number of facets of P is exactly the minimum, let's say R, such that you can prove all of the theorems that are true for P using only R functions. You starting with R non-negative affine functions, you can prove everything. So this theorem implies this. Okay. But we already said that this is not necessarily the object we want to think about. We want to think about whether there is a lift of P that has a small number of facets. And this is the content of, Yannakakis' factorization theorem. So let me now give an analogous characterization of sort of the minimum number of facets in any lift. It should be obvious that this is a much more complicated object. This is a much more complicated functional than this one, because here you're taking an infimum over all possible lifts of P. Here you have P. You just look at it, you see how many facets it has. Here you're taking the infimum over every possible lift of P. But okay, so let me state Yannakakis' theorem in this framework. Which is that the minimal number of facets in a lift of P is okay. Actually, let me just motivate this for 1 second. Just observe. Okay, let's just put a little box here, a little random observation. Observe that the non-negative affine function on P are precisely the same as the non-negative affine functions on the vertices of the polytope. It's clear that that if you're non-negative on P, then you're non-negative on the vertices. But conversely, if you have an affine function that's non-negative on the vertices, it's also non-negative on P because you just write a point in P as a convex combination of the vertices, and then use the affinity of the map to say that it must also be non-negative on P. So the point is that an affine function is non-negative if and only if it's non-negative at the vertices, which means that in order to prove to you that some function here is non-negative on P, I don't have to prove that it's non-negative everywhere. I just need to show you that it's non-negative at the vertices. So this leads naturally to the same setup, except now I only care about affine functions that are non-negative at the vertices. And now the vertices have it's just a finite set. They have no linear structure. So we can ask, did you prove them all of those theorems using a small number of functions, but the functions no longer are required to have any structure except to be non-negative, such that Fi from the vertices maps the vertices to non-negative real numbers. Okay. So this is the content of Yannakakis' theorem, that you can think about the smallest, the minimum number of facets in a lift for P as just the minimum number of functions, non-negative functions on the vertices that you need to generate all of the affine functions that are non-negative on P. This is not, let's see, probably actually from, once you have actually this red statement, this one is actually not so hard to prove, except in terms of notation. You have to remember how matrix multiplication works, which is tricky. It was a joke at my own expense. It is hard to remember because it's, okay. But now let me just say how this connects to what Reka said yesterday. So to this matrix P, now we can associate, to this polytope P, we can associate a matrix. And actually, the way I'm doing it now, it's going to be even a universal matrix. There will not be, there will be a degree of freedom, I guess, in which you can compute the rows. But let's define this slack matrix for P as the rows are indexed by F's. I'll put the domain in a second. The X's are indexed by vertices, and you just evaluate the function there. Where F ranges over the restriction of all affine functions that are non-negative on the vertex set, and P ranges over this. This is a matrix we associate to the polytope P. And it's one particular slack matrix for this polytope. By the way, of course you see that the matrix is uncountably infinite. Don't let this bother you because we already see that the matrix has it has finite rank. So sort of most of the vast majority of the rows are not interesting. Given some subset of interesting rows. The other ones are written the combinations of them. But now you can restate this fact in a different way. So this Yannakakis factorization theorem is equivalent to saying that the non-negative rank of this matrix, there's no X here, just this matrix M P, is equal to the minimal size of a lift for P, which is equal to this one. This is basically, I want to say that this quantity here is precisely this quantity here. And actually, we can just see it. So let me, in the process, let's remind ourselves what the non-negative rank is. So the non-negative rank in general of a matrix M is the minimum R, such that we can write Mij as, let's write it as, these are just r-dimensional vectors, but it's not, okay. If I just wrote that, that would be the definition of the rank of the matrix. That would be the rank over the reals. If I require those vectors to be non-negative, I get the non-negative rank. And now you can see, okay, so now what is the, let's look at this matrix. This is the, let's make it clear, this is the definition. What is this matrix, like what is this matrix telling us in this setup? So, suppose we have a non-negative factorization, what does it look like? Okay, so let's say f of x is just the fx entry of this matrix. And now, if this matrix has non-negative rank R, we can write this in the following way. Ui f vi x. And for some reason I used capital U and V here, because I thought momentarily it would make things simpler, but now it's confusing me. Because capital letters look, you know, I wish I had used lowercase u and v, that's all I'm saying. But nonetheless, the equality is, I mean, the mathematical content is the same. It's only some aesthetic issue I was having. Right, so the point is, I mean, this is the factorization. This is the, if we have the matrices u and v, then, you know, ui, this is the inner product of ui and the ith row of u and the ith column of u. Okay, or it's just this setup here. So is it clear that the factorization is exactly saying that the fx entry is the inner product of the f row, or of there's the issue, I see. It's annoying because these indices are not the same. So let's, so aesthetics did kind of matter in the end. Let's just continue to use f and x. So the point is that, the point is that this index I was very different from this index I. This I was actually a function and this one is okay. So now, sort of this way. For every f I have a vector, and for every x I have a vector. And if they sit in r dimensions, it exactly means that f of x can be expressed this way. And now you see that what it means is that, you know, if the non-negative rank of this matrix is r, then it's exactly saying that every function sits in the cone generated by the function, the vi functions. Okay. So the point is that the rank of this matrix is r if and only if, I mean, I'm showing you that this quantity here is equal to the non-negative rank of this matrix. So the non-negative factorization is exactly just a way of saying that you can write all the non-negative affine functions on V as non-negative combinations. And if you think about it again in terms of proofs, the VI's are the axioms and the UI's are the proofs. So if you want to prove to me that that f is non-negative, right? So then you write it as a non-negative combination of the VI's, which are are assumed to be non-negative. So now okay, good. You showed me that. Now you certify that f is non-negative. Okay. So does the setup make sense? The main point is just here, like the connection between optimization and proofs, and the fact that the non-negative rank is a way of restating the fact. The non-negative rank of slackening is just a way of restating the fact that you want to generate all of these functions using a small number of functions. The rank is the smallest number r, such you can generate them using only r functions. Are there questions? Because now I want to do the semi-definite analog of that. What the main where m sub e is defined up there. Well, this is the main takeaway. Okay. So let's do the semi-definite version, and then we can get started. Okay, so equivalently we can define the sort of the smallest size of a semi-definite lift of this polytope. So I wasn't going to do it, but let's actually define this. Okay, so the point is that this captured, this notion captures P as the projection of the feasible region of a linear program. That's sort of the point. So now, if we want to think about semi-definite programs, we would like to think of a notion that captures, we would like to think about capturing P as the projection of the feasible region of a semi-definite program. So let's, so this is the minimum R, such that there exists, let's say, some Q, an R-dimensional spectrohedron. We could define it yesterday, but I'll remind you in a second. Does it bother you guys? I mean, do you guys refer to these things as R-dimensional? Because they're not really, so it's weird. What's not with that?
Suns are.
Say it again?
Suns are.
Oh no, just yeah, I see. The size R. Okay. There is a size R spectrohedron. We'll say what it is in a second. That linearly projects to P. And the point is that spectrohedron is exactly the feasible region of a semi-definite program. What is it? Okay, so I'll use the same notation as yesterday. So this is these are going to be n by n real symmetric matrices, and then S plus n. These are the positive semi-definite matrices. So just as a and then here's a definition of a size n spectrohedron. It's exactly something which is the intersection of the PSD cone with W for an affine subspace W of symmetric matrices. Okay, so you just take the PSD cone and intersect it with the affine subspace. That's the feasible region of a semi-definite program. And so now the PSD lift size of the polytope is just the minimum R, such that there exists a size R spectrohedron that projects to P. So it's exactly, again, it's asking for a small, this one is asking for a small linear programming characterization of P. This one is asking for a small semi-definite programming characterization of P. And I guess as an exercise, you can prove to yourself that that really we did get some more power from using semi-definite. Okay. And so now the question is sort of what's the analog of the factorization theorem in the setting of semi-definite programs? Okay, so let's call it the SDP YFT. So definitely, there were sort of converging sets of interests in the world that arrived at this, sort of like thinking about these generalizations at the same time. So at least, so there's two groups of authors who sort of observe that Yannakakis' theorem extends at least to the PSD setting. Sort of Gouveia, Perillo, Thomas, and also let's say. I'm just going to say these authors' names one time. So Fioriti, Massar, Calcutta, Tavari, and De Wolf, and then I'll just maybe use like F plus to denote them from now on. But what's the semi-definite version? So the one thing we need is instead of non-negative rank, we need to talk about semi-definite rank. Then we can write this down. So let's define I'll define the semi-definite. The positive semi-definite rank, and then we'll write the analog here. So I will continue to index them by f and x, which is odd, but maybe for consistency of notation. So it's the minimum r, such that we can write this is just, I mean, f is indexing the rows, x is indexing the columns. You could think about it as I and j or s and t, a and b. Really, any choice of Arabic letters. You can use Greek letters. Okay, but it's we require that the fx entry here can again be written as an inner product. So here it was just the inner product of non-negative vectors. This is now the Frobenius inner product on symmetric matrices. Okay, where those are R by R PSD matrices. So the point here is that for all f and x, those things are sitting in the cone of R by R PSD matrices. So this is the notion of PSD rank of the matrix. So it looks exactly like non-negative rank. It's an inner product, and you write the fx entry as an inner product of two vectors uf and vx. But now instead of the non-negative orphan, you're allowed to write things as PSD matrices. And again, it should, okay, so one thing you can see is that this non-negative rank corresponds exactly to PSD rank if you restrict yourself to diagonal matrices. So for diagonal matrices, you get back here. And then the SDP factorization theorem is that all this characterizes the size of the smallest SDP lift. So the size of the smallest SDP lift of P is precisely the PSD rank of MP, where you should recall that this is the slack matrix we defined over there. Okay. And this is why now we will no longer see this definition. We will no longer see this notation phi bar SDP. Because now we're just going to care about the PSD rank of associated matrices. But the point is that you have this at least for many problems, extremely powerful model of computation, trying to characterize polytopes by semidefinite programs. And now you can sort of that seems difficult because I mean there's lots of different semidefinite programs, and now we reduced it to thinking about sort of a different problem, which is this odd notion of rank for a non-negative matrix, which is also, I guess, not so simple because there's infinitely many different possible factorizations. But okay, but now let me just tell you what's the analog here. So we said that the non-negative rank we can just think of it as the minimum R, so you can generate all of the non-negative affine functions using a small, just on the vertices, using a small number of functions. So there's a similar thing for in the semi-definite case. So you could think about, okay, so again, let's say that for a subset of functions. So when I write L2 of V, let me just put the definition over here. I just mean the Hilbert space of functions on vertices. Everything is finite dimensional here. So I'm just really writing it for I just want to think about this as a vector space of functions. So for a subset of functions, let's define the sum of squares cone over W. Okay? So it's the analog of, if we have here we have a finite number of functions and we take non-negative combinations. Now we'll talk about taking some subset of functions and thinking about all of the non-negative functions that can be generated by sums of squares of things from W. So it's a set of all functions that, let's say, are like sum of qi squared, such that all the qi's sit in W. This is the sum of squares cone over W. So you start with some functions, and then you you sum up squares of those functions. You get some other functions. That's the sum of squares cone. And now, here is the natural analog of this quantity. Here you're trying to prove all of the theorems using a small number of axioms. Here you're doing the same thing, except that now your proofs are more sophisticated. Okay, so let's write down the analogous. One thing you might do. So let's think about the minimum of R, such that we can generate all these functions using sums of squares from W. But now we allow W to be an entire subspace of dimension at most R. So the point is, here the axioms are just non-negative functions, and you can take finite combinations of them. Here now your axioms are, well, you can think about your axiom as a basis for this subspace, but you get some R-dimensional subspace of axioms. And then the things you can prove are this, everything is a sum of squares of things from W. Well, for the sake of notation and everything, it would be great if this was the PSD rank of M. Okay, but it's not. But okay. So what I mean, it's essentially is. So let me write the relationship that's satisfied here. Okay. So first of all, and I'll explain why it's. This is probably at most rank squared. Okay. But this is not important because we're not going to use this anyway. I just want to sort of think. First of all, we're going to try to prove exponential lower bounds on the rank or super polynomial lower bounds. So this square is not really germane. Why do you get a square? If you really wanted to get this exactly, you should have taken the QIs not to be real valued functions, but instead taken that you should have instead taken. So if you want the exact analog of this, you should take sort of you should have taken your functions to be things that have values in an R-dimensional space. And if you did that, and then you replaced the QI squared here by the norm of QI squared, you would get exactly the PSD rank. But this is an aside. Like I wish I hadn't even written it, but it's too late. It's written. Okay. But the point is, I mean, up to a square, this is the thing which is analogous to this. So we're giving ourselves a more powerful proof system. The set of things we want to prove are the same. We want to be able to assert the non-negativity. We want to be able to assert the non-negativity of affine functions that are non-negative on the vertices. But the way we can prove things is now significantly more powerful. Because instead of just having a finite number of axioms, now we have an entire subspace. Okay. So the point is, okay. So I mean, okay. So now we set the stage. Now I can tell you what's our goal in these lectures. Are there any questions about this? I mean, really, it's just sort of like somehow this is the simplest way to think about what's going on here. You care about semidefinite lifts, but at the end of the day, what you get is just a problem about, I have some family of functions. Can I certify the non-negativity of those functions by writing them in some small, in some canonical way, where the canonical way doesn't require the proofs to be too complex? So here the point is that, if I have a low-dimensional subspace of things, I take sums of squares. That's a nice way of writing them. And of course, as Laura mentioned yesterday, these certificates we can even it's implicit in everything we said, but we can search for them in time polynomial in the dimension here. So it's not just that they exist. If they exist, if certificates of this form exist, then semi-definite programs can find them without taking too much time. Okay, so what's the by the way, you would be. I mean, the natural thing here is to be scared because, like, what the, but like, I mean, okay, like this. I mean, this still looks like a complicated object. Like the set of affine functions that are non-negative on the vertices. But it turns out, for the polytope we're going to study, that this is a very nice class of functions, and the whole thing reduces to, just reduces to a very appealing and seemingly, it should be simple, but just a very appealing problem. Okay, that we'll get to in a second. But what's our goal? Well, we define a notion of complexity now, which is this the size of PSD lift of a polytope. And a natural goal then, this is a powerful model of computation. It would be nice to prove that P is not equal to NP in this model of computation. So that's our goal. So to prove that SDPs cannot prove that P is equal to NP. Or, I guess, prove that P is not equal to NP for semi-definite programs. Okay, just basically, we want to show that, if we took a polytope underlying an NP-hard problem and the PSD lift size was polynomial, this doesn't quite imply that P is equal to NP, but this implies that NP has polynomial size circuits. So this definitely shouldn't happen unless the world is very different than we expect. So this is our goal, and in order to achieve that, we're just going to consider one particular family of polytopes, and we're going to try to prove that they don't emit any polynomial size PSD lifts. That's the goal. And what are those polytopes? So let's define them. Okay. Use the correlation polytopes. So this is the convex hull of all rank 1 binary matrices. So you just take 0, 1 matrices and take XX transpose. Right. This is the matrix where the ij entry is xi xj. And just take the convex hull of those. That's the correlation polytope. And the reason for considering this polytope is, first of all, it's the same as the CUT polytope. Okay, so the CUT polytope is a natural thing that you really might care about. But if the extension complexity, if the size of the smallest SDP lift of this thing is large, it implies by reductions that that the same thing is true for lots of polytopes underlying NPR problems. So TSP and the CUT polytopes and stable set polytopes and so on. If this is large, then sort of the same thing is true for those. Okay? So the point is, by proving lower bounds for this thing under reductions, the reduction for the CUT polytope is trivial. This is the CUT polytope in n+1 dimensions, but defining the CUT polytope is not really going to help us. So we'll just look at this one. But the point is that if we can show that this thing doesn't have small lifts, then it implies that lots of other things don't have small lifts. Good. So let me state what's the two theorems. Okay, so first of all, Fiorini like that. Okay, we'll see. So Fiorini et al. Proved that this thing has a large non-negative rank. Okay, so I guess let's I lied, right? I told you this notation wasn't coming up anymore. But that the size of the smallest polyhedral lift of the correlation polytope grows like exponentially in n. Okay. So this, this by the way, this sort of solved a long-standing open problem. It was open for 20 years since the foundational work of Yannakakis. And then what I'll talk about is names. Todd, Roddy Bender, and Dave Storr from essentially last year. Troy might have to help me out with the bound. Tell me what the bound from our paper is. Okay, let me write something and then I'll look at Troy's face to see if he reacts. Okay, it's okay, so I wrote there n to the 2/13. Is that the
That's the original. That's what you say in your paper.
okay, so that's definitely true. I guess you can also do doing 2/11.
That's right.
So in our paper we bound square root of n by n to the 3/2. And Troy pointed out that if we bound it instead by square root of n, we get a slightly better upper bound. Here, let me try to write this to. Okay, so it doesn't matter. It's some power that's n to the 2/11. Okay. Yeah, and this is going to be our. So this is our goal. But now, okay. So now in the time remaining, let's just sort of set up exactly what we need to do, and it's going to reduce everything to a very simple, easy to say problem. So what we're left to analyze is, what are the non-negative affine functions? What are the affine functions that are non-negative on the correlation polytope? I mean, that's the sort of you look at these things, but this is really what we care about. What are the inequalities that hold for the correlation polytope? The linear inequalities. If we can write down what those are, then at least we've reduced the problem of proving something about every possible semi-definite characterization of this polytope to just something about whether a certain family of functions can be generated by sums of squares of other functions. So let's just explore, and it's very simple, the set of all the linear inequalities that are valid on the correlation polytope. So this is going to be, so let's do this. Sorry, I don't want to write too close to the top here, so let's try again. Define QML plus of n. Okay, so this stands for quadratic multilinear positive n dimension. It's just the family of all functions on the discrete cube that are non-negative and quadratic. So it's just it's all of the non-negative quadratic multilinear polynomials. They're not so many, but they're infinite many others. Does it make sense? I mean, e.g. Here's a quadratic function that's non-negative, in fact, on all of our n, but it's also non-negative on the discrete cube. Okay, that's an example. Okay, so given that, now we can define. Okay, so let's define our matrix, which is indexed by such functions, and then the elements of the discrete cube. It's just the matrix where at f and x you get. Let's put a little n. Okay, so our matrix Mn is exactly this. You just get for every quadratic multilinear function on the discrete cube, and every vertex and every point in the cube, this matrix just has the evaluations of all those things. So it's just the values of all the non-negative multilinear functions on the cube. That's the matrix. And now the claim is that this is the slack matrix for the correlation polytope. So I claim that the set of all affine functions that are non-negative on the correlation polytope exactly correspond to the set of quadratic multilinear functions that are non-negative on the discrete cube. And the only reason I wrote V there is because, again, well, actually, if we think about the matrix as a function, then I'm fine. So, because then I don't have to worry about permutations for those. So is it clear that I'm claiming that this is the slack matrix? Okay. So what it means is that so let's consider what it means for trying to prove a lower bound. Then our question just becomes can all the quadratic non-negative functions be written as a sum of squares of some functions from W from a low-dimensional subspace, right? So the point is that once we prove this claim, then our question of looking at the size of PSD list of the correlation polytope through sort of through this connection just becomes right. The point is our A plus of V just becomes QML plus N. So this is the question: can you prove all the non-negative quadratic? Can you certify non-negativity of all the quadratic multilinear functions on the cube using sums of squares from a low-dimensional subspace? So there were lots of definitions, but at the end of the day, it's like a very simple question. It seems like it should be easy to resolve. So this is going to be our starting point next time. But so for now, let's just prove the claim. So I guess the first time if you see this claim, the one thing you wonder is like, before we were talking about affine functions, so like linear functions, and now we have quadratic functions. Where does the quadratic thing come in? So let's see it. So let's just take, let's consider some f in this family. Consider f in Q L plus n. So we can write f to degree 2 polynomial. So let's write it as some constant term plus some ij x I x j a I j. By the way, here I use the fact that the thing is multilinear because I don't have any. Syntactically, I don't have any degree 1 terms, but of course xi squared is equal to xi, so I have degree 1 terms there. And the point is just now, if we define A to be this matrix of coefficients, then f of x at some point of the discrete cube is exactly equal to A0 plus the inner product of A and xx transpose. So the point is, this is really just the Frobenius inner product between the matrix XX transpose and the matrix A. Somewhere all ij of aij times the ij entry of this matrix, which is xi xj. And so the point is that, if this thing, so this thing is non-negative on the discrete cube, so this is going to equal to 0. So that implies that this thing is greater than or equal to 0 for all x in 0, 1 to the n. And then let's just and then that implies that this is a valid linear inequality for everything in the correlation polytope. Just because, as we said, if we prove an inequality at the vertices, then we get it everywhere. So since if f is non-negative on the discrete cube, so the point is this. I guess the point is that this is now a linear inequality upstairs. So now every quadratic f corresponds to, every quadratic non-negative f corresponds to a valid linear inequality in the correlation polytope.
I guess it's still plus, right? A0 plus.
Oh, yeah, I don't know why it says minus. Good point, yes. And, you know, I guess we, you know, should just do this. Oh, yeah. Okay. I mean, we only need one direction, but this was a characterization. It's just we're just rewriting things here. So this was, conversely, if we have a valid linear inequality, then it's valid at the vertices, and from it you derive a quadratic function. So this is really, you know, these really describe all of the non-negative affine functions on the correlation polytope. Okay. So good. So that's it. So I mean, that's, you know, the main point is that just what we need to export for tomorrow is this question. You know, can all of the quadratic multilinear functions be written as sums of squares from a low-dimensional subspace? It's a very simple question to state. So let's stop there for today.
Any questions for today?
Any like thoughts about, like, does it look? It looks very simple, right? I guess the question is, does it look obviously impossible or obviously like trivially possible? I mean, we know the answer, so. I guess it looks easy because, in some sense, because these are quadratic functions, so they're like already low degree. So maybe you don't need very high degree to write them. I don't know. When I say easy, I mean maybe it looks like you can do this with a low dimensional W. On the other hand, well, we'll see.
I think it's always kind of scary when you don't know what W can be, right?
Yeah, but with so much, the point is there's so much symmetry here, right? You can, that like, it doesn't, could you really have such a clever choice for W? Because there's so much symmetry, like why would there be a, okay, so we know there are situations where even when, you know, when this matrix has a symmetry, there exists, you know, the best sum of squares cone is actually asymmetric, so we know that can happen. So actually asymmetry can help to lessen the size of the dimension of W. But
So what is an example for that phenomenon?
So what is an example for that phenomenon? I mean, the most convincing example, or maybe the most interesting, is that it happens for the perfect matching polytope. So the point is that you can define. So this was the notion of a lift. You can define like the notion of say like a symmetric lift or an equivariant lift as a lift where upstairs you respect the symmetries that are going on downstairs. And for the perfect matching polytope, it's known that the best asymmetric lifts are significantly smaller than the best symmetric lifts. So Yannakakis actually proved a lower bound on the size of the smallest symmetric lift for the perfect matching polytope. And you can, I mean, both are exponential, like the lower bound is exponential and the upper bound is exponential, but the exponent, like the number c, the exponent is smaller in the asymmetric case.
Mm-hmm.
And okay, and it's for a pretty interesting reason, which is that if you take some, here's one way to construct a W. Just start, define some distribution over functions, and just start throwing them in at random into a subspace. And you take the sum of square cones. So you take the span of those functions and then the sum of square cone of the span. And the point is that, like, I mean, I guess sort of there are multiple ways to represent the same function as a sum of squares. So if you start, throwing all these axioms in, they start combining together, and then sort of, they generate kind of. You can generate things since you can write functions as multiple different ways as sums of squares. You can think that sort of like every time you throw in a new function, you cover a little bit of the remaining things you haven't covered yet. And this actually, for perfect matching, this actually helps reduce the size. Basically, because I guess the natural lift of perfect matching, or the natural way to write it this way, every non-negative, every non-negative function on the perfect matching polytope has multiple representations, and so the symmetric lift is redundant. So if you sort of just say, if you randomly downsample the symmetric lift, then you get an asymmetric lift, which still manages to express everything as long as you sample enough. You see the